We've been driving a car in the desert for hundreds of years now with our foot floored on the pedal and not looking out the windows and with our hands off the steering wheel, just driving. And we see a cliff coming, right? The idea that we should look at the situation of climate change and think like, oh my God, there's a precipice coming and bad things are increasingly going to be happening. And our job is to take hands off. No, it is way too late to think we can be pristine. The world is no longer pristine. Our job now is to grab the controls, and instead of driving in a random direction with the pedal floored, we've got to drive the system intentionally and wisely.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. I'm here with Allan Adams, the founder and CEO of Aquatic Labs. Allan and his team are developing scalable technology to measure important data about our oceans, including carbon, nutrients, and biodiversity. I'm particularly excited to hear Allan's take on a recent announcement they've made about a sensor that could really change the game for ocean-based carbon dioxide removal, or marine CDR. Marine CDR is promising because by harnessing the Earth's natural processes, we could potentially do more carbon removal with much fewer resources than engineered approaches like direct air capture. But scaling this today is limited by the cost and complexity of measuring the process. This new sensor from Aquatic Labs looks like a really promising way to solve that problem. I know my team at Synapse that works on CDR is really excited about it. It fits in the palm of your hand, measures total alkalinity in seawater in situ in real time with no reagents, no microfluidics, and at a cost that makes it very scalable. Allan started his career as a theoretical physicist, earning degrees at Harvard, Berkeley, and Stanford. He then spent 15 years at MIT, including time as a professor of physics and as the PI of the Ocean Future Lab. He also spent 5 years as an adjunct oceanographer at Woods Hole prior to founding Aquatic Labs in 2022. I'm excited to hear how that blend of theory and direct experience with the ocean has brought him to where he is today. Allan, it's really a pleasure to have you. Thanks for joining.
Dylan, thanks so much for having me on. I'm really excited to be here with you.
I am curious how you made that transition from this, what looks on paper like a very sort of, theoretical physics, this very sort of theory-based focus, to something that looks to be very hands-on and experimental, focused on kind of real-world impact. What was that move like?
It's the classic move, string theory to oceanography. It's a pretty classic transition.
Yeah, right.
So it's a long story, but I'll give you a sort of intermediate version of it. So I was trained as a theoretical physicist. I taught string theory at MIT, loved it. And I still deeply love theoretical physics. But I was very lucky. I got to teach a big intro class. And as a result, all sorts of crazy things happen when you teach intro quantum mechanics at MIT. So one of the truly crazy things that happened was I got an email one day saying, hey, Professor Adams, you're teaching a big intro class. We run the Latka-Hamantash debate at MIT. Would you be interested in presenting for the Latka-Hamantash? I don't know if you know what the Latka-Hamantash debate, but I certainly didn't. So it's a debate started in the 40s at the University of Chicago where you're supposed to use the rhetorical tools of your discipline, Slavic studies, math, whatever, to argue for the supremacy of either the latke, potato pancake, or the hamantash, a triangular cookie from Purim from the Jewish tradition. It's tongue-in-cheek. It's meant to be truly joyous. It's hilarious. There's a Latka-Hamantash debate all over the universities all over the world. So I got invited to give this talk, and obviously latke, potato pancake, it's a fabulous thing. But I was really struggling. This was into 2011, 2010. How am I going to use string theory to argue for the clear supremacy of the latke? And the answer came to me in a flash, I should show data from the greatest physics experiment ever conceived, the LHC, the Latka-Hamantash collider. But how am I going to get data? And every time I walk into work, I pass by the Edgerton Center for High-Speed Imaging. These are the people who invented high-speed imaging. So I sent an email to the directors. Dear Director Bales, I understand you teach people how to use high-speed video cameras. Could I borrow one and learn how to use it? And he wrote back and he said, Dear Professor Adams, I'm sure we can find a way to help you, but for what research purpose do you need high-speed imaging. I was like, well, so I said, I'd like to collide potato pancakes and cookies at high speed, send. He wrote back and said, awesome, come to my office on Friday. So we did, we collided them. I gave the talk. It was great fun. But in the process, I got to know the high-speed imaging people. And the high-speed imaging people at MIT are amazing. And meanwhile, I have a good buddy who was a dive photographer. I was like, oh, peanut butter and chocolate. So I got them both at my house for brunch one weekend. And a couple weeks later, we ended up at the New England Aquarium with $500,000 of camera equipment and start filming cuttlefish catching their prey. And this was super fun. One thing led to another. We filmed the TV ad campaign when the giant ocean tank reopened at the New England Aquarium. We started doing documentary work and working for museums. And all this was like high-speed underwater photography. This was my weekend gig, right? During the day, I studied seven-dimensional black holes. And on the weekends, I did underwater videography. And in 2013, two things happened. One, I spawned. Right? My first son was born. He was awesome. And the second thing was I got invited by the aquarium to go on an expedition to Fiji. And I went not too long after he was born. And that was amazing. I had no idea how emotional it would be. And every night on that boat with a bunch of oceanographers, every night on that boat, all I could think was, that was the most spectacular soft coral I've ever seen. And by the time my kid's old enough to see this, it's going to be gone. And that was 11 years ago. And since then, we've lost 20% of the world's corals. Every night I was thinking that. And on the flight home, I was like, what the hell am I doing with my life studying seven-dimensional black holes that don't exist? Like, I love the theoretical physics, but something broke right there. Something really changed in me. And by the time I got back, I was like, I don't know exactly what I'm going to do or how I'm going to do this, but this thing that I do in my spare time, I think I need to turn this into what I actually do for a living. And it took a few years to figure out how to do that, but I eventually switched over, started a lab. God bless MIT, they'll give you enough rope. Started a lab as a theoretical physicist building cameras and imaging systems for ocean exploration, which was awesome. I taught one of the most fun courses I've ever taught and met people, got to know people, started building more and more detailed instruments and got a joint appointment at Woods Hole. And after a few years at Woods Hole, which was awesome, I love that place. The people are amazing. It's one of the great achievements, I think, of this country is Woods Hole Oceanography. It's an amazing place. But we would build instruments. And we'd build incredibly awesome instrument, like a deep ocean radiometer that measures individual solar photons 800 meters underwater. It's 13 orders of magnitude of dynamic range from the surface to the bottom. It's super cool. And when the paper comes out for that sensor, there's like 7 people in the world whose toes will wiggle with excitement. And no one else is going to care, right? And I got into this for impact. And I got so frustrated because I saw the distance between what I saw as possible to build and what we could build inside the academic constraints and confines that I quit. I quit Woods Hole. I quit my job at MIT and started Aquatic Labs. And we're here to build the kind of scalable tools for industrial scale problems like carbon sequestration, where you don't need 1 or 2 of an instrument. You need hundreds of thousands over the next decades.
That's an amazing answer, actually. And I love the story. And was ocean sequestration specifically something driving your interest in starting your own company and building more scalable sensors? Or does that same kind of mindset apply to other challenges you were seeing in the ocean?
It really was broad. So here's the thing. If you sit back and think like, what's possible to measure in the ocean? There's a tremendous amount that's like if you go to a factory on land, there are temperature sensors scattered everywhere like candy because you want to know when that pulley starts to fail. You want to know 6 months ahead of time so that you can deal with the supply chains and make sure you have the process and don't get surprised and have your whole factory shut down for an afternoon. And the industrial activity we do in the ocean is increasingly approaching industrial activity scales we do on land, but the measurement isn't there. And the measurement there, it's for basic things like temperature, and it's for extremely esoteric things like alkalinity, and it's for biodiversity monitoring for marine protected areas. All of these things we do not see into the ocean. We do not measure, and we don't have the ability to measure on any sort of scale the vast majority of things that we could actually do something about. And so part of that is climate change, like carbon sequestration. Like I can go off on this, I'll resist the urge. The ocean is an incredibly valuable ally in carbon sequestration for very good reasons. And yet measuring the carbon there is like measuring invisible gold. Like you just can't see it. And so that has to change. So yeah, carbon sequestration was one part of the story and increasingly has become more and more my North Star. But from the very beginning, it was really about changing the way we measure 1 or 2 things using ships, using expensive assets. Every data point costs you $1 million. That's how oceanography has worked for decades, for centuries at this point. And that was what hurt, right? That needs to change.
Right. The sensors existed, but in the form of very expensive laboratory scale equipment.
Exactly.
And just to give that a second, is the difference between our ability to measure in the ocean and our ability to measure on land purely about sort of the environmental challenges of measuring in the ocean? Or is it about demand, or why is that?
Yeah, that's such a great question. Well, it's a mix, right? So on the one hand, first, anyone who's done anything in the ocean, even if you've just played in the surf, you have a sense that the ocean wants nothing more than to break your toys and steal your lunch money and send you home crying. It is a harsh, cruel, nasty environment that just wants to destroy. It wants to grow you, it wants to break you. And so it's much, much more cruel environment than, say, in a factory on land. It's just operationally very complicated. The second thing is that the chemical environment is nasty, right? It's toxic. It's got the caustic chemistry. It wants to dissolve away your electrodes. It's a very harsh place for electronics. And forget going deep, you go thousands of meters deep and the pressure is really high. But the other thing is, as you're alluding to, there exist gigantic industrial systems on land where there's a well-defined who pays for what through a whole chain of markets that exist. And for the most part in the ocean, that doesn't exist, right? That's just starting in a lot of applications. Carbon sequestration. In the ocean, it's a great idea, but it's not yet truly a market. Aquaculture is a market, but the margins are really tiny. That's, exploring. So a lot of what we're seeing is expansion of markets, of industries into ocean adjacent and directly out into the ocean, and that's new. So that's part of the reason too. There's an additional thing that's often underappreciated, which is that the low-hanging fruit for a lot of commercial ventures in the ocean ends up being military and oil. And that's great, except that they're very specific kinds of customers. And I say this with an eye towards startup founders out there who are thinking about their markets. Here's the thing that's really dangerous. I think that's dangerous is if you turn out, you're trying to build something that could scale, but you've got a customer who really just wants 6 of them and doesn't care what they cost. Well, it's very tempting to go after that and sell 6 of them for $1 million a piece. And you've suddenly raised your Series A. And that's fantastic. The problem is no one else is going to buy 6 of them for $1 million each. And so now you've been captured by this little tiny community, which doesn't allow you to go to scale. You may be very financially successful, but you're not going to scale. And the problems that I care about, carbon sequestration, biodiversity monitoring, these are problems that by their nature require scaling. And so we're trying really hard to avoid being drawn into military and oil, not because of deep objections to what they're doing, because military is actually really important, but because it's a dangerous way to go as a startup that wants to scale.
Yeah, that's really interesting. And you can't have sort of global climate impact with 6 sensors or with a small number of very expensive sensors. I hope we talk about that a little bit more. You said that carbon sequestration has increasingly become a focus. I'm curious, what has been changing over the time since you founded the company to make that so?
I think there are a couple of things. First of all, I thought a lot of the measurement problems were just too hard to tackle in the near term. And the measurement challenges are really hard, but they're not too hard to tackle. And that's part of why I'm so excited about what we've been doing with our alkalinity such. So that's one thing. There's technical reasons. But another thing is that, look, it took me a while to come around to this. I was raised in an environmental movement which defined our moral responsibilities as taking our hands off of the system, right? Environmental responsibility means stop the bad things you do. And this is the Sierra Club. This is the Colorado River Watch where I grew up. This is respect and preserve the ecosystem, leave no trace, and just step back. But here's the thing, and it took me a long time to come to this. I came to it kicking and screaming, but I've become very strongly committed to this point of view. We've been driving a car in the desert for hundreds of years now with our foot floored on the pedal and not looking out the windows and with our hands off the steering wheel, just driving. And we see a cliff coming, right? The idea that we should look at the situation of climate change and think oh my God, there's a precipice coming and bad things are increasingly going to be happening and our job is to take hands off. No, it is way too late to think we can be pristine. The world is no longer pristine. Our job now is to grab the controls and instead of driving in a random direction with the pedal floored, we've got to drive the system intentionally and wisely. We are morally obliged, if we care about stewardship and conservation, I believe we are morally obliged to put our hands on the engineering controls of the planet. And when I think about carbon sequestration, the data pretty clearly show that even if we stop producing now, and it's beautiful what's happening with wind and solar, CO2 emissions are going to be going down, fingers crossed. But even if they came down really fast, we're still in a really bad place. We need to be pulling carbon out of the atmosphere. And I think we are obliged. And I look at my kids, I got into this because I spawned, right? And it suddenly mattered to me in a way that viscerally it hadn't before. We owe it to each other. We owe it to future generations to put our hands on those controls. And that is carbon sequestration. That is geoengineering broadly construed. We are obliged to do that, I believe.
Yeah, it feels like enough of the market is kind of understanding that and starting to make these voluntary purchases. And if you believe any of the sort of projections, like this is just going to continue to scale at a pretty incredible rate. And then help us connect the dots. Like, what's the importance of a total alkalinity sensor in this whole picture? We're taking CO2 out of the atmosphere. Why do we need this little sensor that measures alkalinity of the water?
Yeah, that's such a great question. So first, let me just sort of, for folks who aren't familiar with alkalinity, let me give you a quick definition of alkalinity, tell you a little bit about how we measure it and why this is different, right? And then I'll bring that into why does this matter for carbon sequestration, which it deeply does. Okay, so first, what is alkalinity? Alkalinity is a property that if you pour acid into some seawater, naively, the acidity of the water is just how much free hydrogen is there, morally speaking. And as you pour water in, just by volume, you've got something that's neutral, you've got some acid, you pour it in, and it'll be a little more acid. It'll be a little more acidic. But it turns out that with seawater, it's not as acidic as you would have guessed. You pour in the acid, it turns out that the seawater as a result is less acidic than you would have guessed. And the reason for that is really beautiful, is that there are a bunch of dissolved chemicals, ions in the water that buffer the alkalinity, that basically grab those free hydrogens and suck them up into other chemical compounds. And so there's less free hydrogen lying around. It's just less acidic. And that's really cool. In fact, that's why the oceans have the almost neutral acidity that they have, is because when it gets a little too acidic, then that water dissolves the rocks in the crust of the earth. And then those dissolved ions go into the water and they absorb the hydrogen and cancel out the acidity. And so if you crank up the acidity of the sea, it will eventually come back down to normal because the rocks will dissolve and buffer out that property of the water to buffer changes in acidity. That is what we call alkalinity. So how would you measure the alkalinity of water, the potential for buffering acidity? Well, the answer is really simple. You take your sample of your water, you pour in some known amount of acid, and you keep doing that until the acidity stops being buffered and it just starts increasing the way you'd expect by volume. Okay, and that's called a titration. You pour in more, you pour in more, you pour in more, and just measure the pH along the way, and you check to see, is it still buffering? Is it still buffering? Or at some point it stops buffering. You say, I've exhausted all of the ions available. I've just measured the alkalinity because it's proportional to the amount of acid that I poured in. Great. The problem is doing that with precision. The kind of precision you need for climate scale action requires taking a sample in a special kind of glass bottle, putting on a stopper with the right amount of air on top, sealing it, shipping it to a lab, having an analytic chemist in that lab carefully take out that sample and slowly titrate in the right amount of exactly measured hydrochloric acid over the course of half an hour. And then in practice, the way you get a result from an alkalinity measurement is you go out with a ship or whatever, you collect a sample, you ship it to a lab. A few weeks later, a few months later, you get some numbers back. And everything in there is expensive. None of that scales. Bottles don't scale, ships don't scale. Analytic chemists do not scale. So if you want to measure alkalinity at any sort of scale, you've got to do something different. Okay, why would you care about measuring alkalinity? Well, here's the key thing for carbon sequestration. The atmosphere is full of a ton of carbon, but it's very dilute. That carbon, that CO2, as it dissolves into the ocean, forms an acid. And that's ocean acidification. So if you had that happening in your body, if you had that happening in your gut, in your stomach, you've got too much acid, what do? You eat a chunk of Tums, right? I've got a big box because I run a startup, so I have a lot of Tums available. And you buffer that acid, try to cancel it off. And that's what the ocean does naturally, dissolves the rocks, and the rocks form basically a buffer in the ocean that cancels off the acid. If the problem with the natural way of doing that, waiting for the mountains to dissolve, is that it takes millions of years. Ocean alkalinity enhancement is a really beautiful way to speed that process up, where you pre-digest the rocks and you crush them up in one form or another, and you add that extra alkalinity to the ocean, like adding Tums to the ocean. It's a little more elegant than that, but morally speaking, that's the right picture. And then the idea then is that alkalinity will buffer the acid and more CO2 will be absorbed from the atmosphere into the ocean. It would make it more acid, but the buffer will absorb that acidity. So the CO2 just keeps dissolving more efficiently into the ocean. And by the way, the vast majority of carbon that we've emitted into the atmosphere, or the majority anyway, has already been absorbed into the ocean, right? The ocean is the leading repository for human-generated CO2 into the atmosphere, that it eventually just goes into the ocean. this method of what's called ocean alkalinity enhancement, you add a bunch of tons to the ocean, morally speaking. There's a couple of challenges you run into. The first challenge is, look, you did something to the ocean, like you poured in a bunch of ground up rocks. Did you actually successfully increase the alkalinity of the ocean? Or did you, in the process, it precipitate out? Did it change through other chemistry? Did it get to the mixing layer in the ocean? Or did it go down to the bottom of the ocean where it's not going to mix with the atmosphere at all? So there are all these basic questions about where did the stuff you put in goes. But then when you think about it from a market point of view, there's another very important question. Imagine I'm Airbus and I want to buy carbon offsets from a company that does alkalinity enhancement. They tell me I've just put 10 million tons of alkalinity into the ocean efficiently dispersed. And that's at $100 a ton, that's $1 billion. Dear Airbus, please pay us $1 billion. Airbus is not going to take that on trust, right? You can't just say you did it. There has to be proof of work. And so the problem is, how would you independently monitor that? Well, the answer is you'd go out and you'd grab 110 million tons. You'd grab a lot of bottle samples and ship them back to a lot of labs and have a lot of analytic chemists run. But none of that scales. It's way too expensive. It's way too slow, and there just aren't the humans to do it. And so there's a basic bottleneck there, which is that if you want to do the monitoring, the proof of work, any of that, the measurement, the systems we have to measure alkalinity don't suffice. Little side note, a similar story goes, even if you're not doing ocean alkalinity enhancement, pretty much any form of carbon sequestration in the ocean, you need to measure either the increase in the ability of the ocean to absorb CO2 from the atmosphere, or the fact that you've injected water that's hypersaturated with carbonate or bicarbonate, any of the CO2 products that you're trying to use the ocean to sequester. But you need to measure the carbon. You can either do that by measuring the alkalinity or directly measuring the carbon. And so many of the ways we have for directly measuring the carbon also depend on directly measuring alkalinity. So alkalinity is sort of a powerful tool for both directly measuring alkalinity when that's the variable you want, but also for probing total carbon or dissolved inorganic carbon, the amount of carbon you've sequestered directly when you can't directly measure that. It's often very hard. I sort of think about this as if you're running a gold mine and someone comes to you and says, I'd like to buy $1 billion of gold. And you say, well, that's great. Here's a big pile of gold. And they look at you funny and say, but it's invisible. And you're like, well, yeah, of course it's invisible, but trust me. I mean, that's the character of the problem that we're facing with carbon sequestration in the ocean. For the most part, these things are invisible at any sort of scale. And so finding ways to measure them is really crucial to the functioning of a carbon market for ocean carbon. And that's what we're trying to do.
Yeah, and the cost of measuring those, and you said this too, but I think it's a really important point because the scalability of this market, of the carbon removal market, depends a lot on how much it's going to cost per ton to remove CO2 from the atmosphere. And that cost of MRV, measuring, reporting, and verifying that you've actually done that, the cost of that measurement is part of that cost. So if you're trying to get down to $100 a ton or $50 a ton or whatever it is, you've got to include that cost of every ton removed, the cost of measurement of every ton removed. So reducing that cost is super important.
Absolutely. And doing so in a way that's trustworthy, because at the end of the day, these are numbers that are going to be reported on the balance sheets of Airbus, Hitachi, Mitsubishi, and they're not going to put anything on those balance sheets that are not auditable with exactly the same rigor as anything else on their balance sheet. So it needs to be quantified at scale, and it needs to be quantified at scale in a way that is auditable and trustworthy and persistent.
Yeah, and the sort of certainty of your measurement increases what you can sell, increases the number of tons you can sell, right? Because you have to kind of sell at the low end of your certainty. Yeah. Also, I love having professors on the show because that was an amazing explanation of all of this. I really appreciate
Awesome.
that. That was really
Thanks,
good.
man. I appreciate saying so. I miss teaching. I really do. Academia is awesome in many ways, and that's the part I miss most is the teaching.
Well,
the
you're
students
still
are amazing.
teaching. Sounds like to me. So you've taken this very manual titration process, glass tubes, shipping things around, chemists working in labs. You've taken this, and you have a picture on this Medium article that we'll have to add to the show notes, but it's this handheld sensor. So I'm really curious, how do you do it?
So what we've tried to eliminate from the measurement process, everything that doesn't scale. You can't have a human in the loop or an analytic chemist or even a me. Like, I'm not an analytic chemist. At this point, I've learned quite a bit of chemistry, but you can't have anyone, no matter how naive, in the loop if you want to do this at scale. We've got to eliminate lab work. We've got to eliminate samples. We've got to eliminate reagents. And so what we've done is we've used techniques actually that go way back to the 70s. Some of the earliest work in ion sensing electronics go back to some beautiful work in the 70s, where some of the basic ideas in this were instantiated. But the basic idea is this. We measure the pH in situ, And we generate reagents dynamically on chip by using some pretty straightforward methods in solid state fabrication and surface chemistry. We do it in a slightly clever way, and we have some secret sauce in there about exactly how we do so. But basically, you generate the reagents there, and then you do the titration directly on the chip. So we're still doing titrations, but we're doing it in a very different way. And in particular, you've got your little sensor that measures the pH, measures the acidity. And remember, alkalinity is answering the question, how effectively does the system respond to the introduction of acid? If I pour in acid, does it just add in volume, or does it get buffered and the pH is less than you would have guessed? And so we do that. We generate acid in situ and we pour it over our sensor in situ. The difference is that we're doing it on a chip, and the length scales here are tens and hundreds of microns. And so the volumes you have to do are incredibly tiny volumes. And the electrical requirements are tiny little bits of power. And all of this is done on a chip in the ocean in real time. So every 30 seconds, every minute, we can get a new measurement of alkalinity, where we're not just getting one number, we're measuring the entire alkalinity, we're measuring the whole system. And along the way, we're measuring pH. And in order to calibrate it, we're measuring conductivity, temperature, and pressure. And all that goes into one device. So that one device that you see in that picture from Manisha's hand, Manisha's amazing. That one device is doing all the measurements required to provide a calibrated answer to the question, what's the alkalinity? And the thing that really blows my mind is, look, we've got this, I love this team. Like, just as an aside, building a startup in a hard tech field is at some level fundamentally about building a technology, developing a product that people want using that. But that's not actually the challenge. The challenge is building the team. Right? The challenge is building a team of people together with the capabilities and the will and all the things you need. And so for me as a startup founder, God save me, I never wanted to be an entrepreneur. Watching this team execute has just been glorious. So I'm just going to make a couple of shout outs. We've got a wonderful analytic chemist technician he spent 15 years out in the world doing alkalinity titrations, DIC titrations on ships all over the world. And his name is Andrew. He's phenomenal. We asked Andrew early on, like, how many titrations have you done, order of magnitude? And he went through it. And he's done, on a busy day, he'd do 30 in a day, which is, each one takes half an hour. So that's not insignificant.
Big
You're
day.
multitasking.
Yeah.
Yeah, big day. Exactly. And that's running multiple setups. And so over 15 years, he's done about 15,000 alkalinity titrations, about 1,000 a year. Our system takes a measurement once a minute. That's 1,400 minutes in a day, order of magnitude, right? And so you hit go, and 1,000 titrations for Andrew is a year's work, and 1,000 titrations for us is Tuesday. And this is a thing I really want to stress. It's not just that we want to build a better sensor to measure a thing. We don't want to build a better pH sensor that's going to outcompete the existing pH sensors because it's a little more precise and a little less expensive. We want to completely change what your assumptions should be about what's possible to measure. We want to be measuring every 30 seconds, every minute. We want to be measuring thousands of alkalinity titrations a day. And we want to do it with climate grade precision. And that's the nut we're trying to tackle. And if it sounds ridiculously audacious, it is. And of course, like, the impossible things are impossible for a reason, but we're doing a really good job so far, I think. And I'm really pleased with where we're going. But that's what we're trying to set out to do.
Yeah, and that reminds me, because I've talked to other companies doing ocean alkalinity enhancement, and my understanding is part of the challenge is you put this stuff in the water, but then the flow of the ocean carries it in different directions. You don't know how well it's getting dispersed. So actually having a grid of sensors or multiple sensors, and I think your Medium post says this, by having multiple sensors, you start measuring the picture rather than the pixel, or the full image rather than the pixel. And I think that ability to deploy multiple sensors over an area in the ocean to really understand what's happening with whatever this material is that you've dispersed through the water seems to be a really important facet of what you're doing.
Amen. Let me give you an example of that. So one of the things we're developing is a new PCO2 sensor, just measure carbon dioxide dissolved into the water in the ocean. And this is a classic problem. It's been done. We're going to do it in a slightly different way. But early on, in fact, this was very, very early on in the company, when we just moved into our new offices here in Cambridge, we have a best-in-class atmospheric CO2 device. It measures CO2 in real time in the atmosphere. Fabulous precision. It's a $15,000 instrument. It just sits there on the benchtop and it just measures CO2 constantly. It's great. And meanwhile, we've been building these little CO2 sensors, and we're building them in ways that should truly scale. And so the very first prototype of that, they were costing us about $50, $100 per CO2 sensor. And we had the data from those go through, wired in a wireless system to a float, and the float then sends the data home. And we decided to do something in our lab. In our lab, we have 10 columns sort of in 2 rows through the lab. And we put on each one 3 CO2 sensors, one at the bottom, one at the top, and one in the middle. And they're sending their data home wirelessly in exactly the same way that the float does that's sitting out in Boston Harbor, right? And so we've got 30 sensors in our lab measuring CO2. Now that one high precision benchtop sensor beats ours by a factor of 5 in precision. I mean, it's a way better sensor. But with our set of 30 CO2 sensors arrayed around the room, I can tell when Lauren walks into the room and goes and sits down at her desk. And I can tell the difference when Oscar comes in and sits down at his desk. And so it may be that the precision is less, but the aperture for you is so much greater when you have dense sensing and when you have spatial and temporal resolution. And we view that as like core for all of the things we're building. We don't want to build an alkalinity sensor that's just a one-to-one replacement with titration systems. I want to put thousands, tens of thousands, hundreds of thousands out into the full ecosystem. Now, that's obviously going to take a long time. That's not something that happens overnight. But that should be on every Argo float, right? Every Argo float should now be a biogeochemical Argo float. Every probe that goes out into the ocean has the capability to have this kind of carbon sensing as well. And we're working really hard to make that possible down the road. So exactly as you say, that sort of scalable sensing really changes the kind of problems and the kinds of measurements you can think about.
Let's talk about that. What's between where you are now and that sort of product that enables that kind of scalability? Because you have this amazing data now in the lab, as I understand it. But what does it mean to take that from something that works in the lab to a deployable product that can be living out in the real world on its own, like we're talking about?
Oh, yeah, that's super scary. So far we've got beautiful lab data. And right now we're in the process of spinning out a series of pilot projects with pilot customers and with some researchers. And the goal there is to, on the one hand, look, the ocean wants nothing more than to steal your money, break your toys, and send you home crying. It's a cruel, heartless place to work. And so we understand, we've like a bunch of us here in the company, most of us have deployed lots of stuff in the ocean and understand just how unforgiving it is. Everything you think will work doesn't, right? It all breaks. And so the trick is not to think that it's going to be perfect or to make it perfect. You got to get out there and put it through its paces. So we've got a lot of learning to do. Our next stage is about learning with field deployments and finding out where we're confused or where we're limited. And so that is, that's going to be the spring and summer. And we're a small startup. We're at 16 now, I think. And our bandwidth is pretty limited, but we do have a little bit of bandwidth left. So if there are folks who are very excited for whom this kind of measurement is really key, get in touch. Like we'd love to talk with you. But this is where we are right now, is piloting with early customers to get real field data. And a kind of a crucial thing, and this is to me a really deeply important part of the whole calculus, not just for us, but the whole field for the market. If we come out and say, look, we did this measurement over the course of a couple weeks, a couple months on this coral reef, in this, on this morning, whatever, and we pulled bottle samples every once in a while. We ran the bottle samples in a Dixon titrator in our lab, and it matches really beautifully. I think outside people should be appropriately suspicious. Like, okay, that sounds great, but that was not independent. Like, we want independent measurements. The same attitude, by the way, is going to be taken by Airbus, Mitsubishi, right? The independent measurement is really important when what you're selling is trust. And in carbon sequestration in the ocean, we're selling trust in the form of carbon, but it's still carbon. So this notion of independent measurement and independent verification, I think, is really key. And we take that seriously. And for us, what that means is these pilot partnerships are not just about us going out and learning how things break. It's really also about getting our customers who are already doing measurements to do the comparison themselves and be able to tell themselves and then other people, hey, yeah, actually, this worked, like against our own measurements and our own bottle samples. This worked well enough or really well or even better than the bottle samples. So that's where we are right now. Oh, it's terrifying times. It's a lot of fun.
Right. And then I guess at some point, there's going to be this sort of engineering challenge of taking something that's working in low volumes and in kind of controlled environments and designing it for high volume manufacturing. I mean, I don't know what sort of scales we're talking about, but you've got to be able to make thousands of these things or hundreds of thousands of these things probably to have the kind of impact we're talking about, right? So it's sort of a whole sort of industrialization, productization challenge of scaling this product, I would imagine.
That's exactly right. And so, not to put too sharp a point on it, Apple decides it wants to build a new thing and it designs its own chips and it builds them. And the reason it can do that is that they know they're going to sell 100 million of them, right? And the reason in academia at Natel I couldn't be like, okay, we're just going to build our own chips and do this development arc, is that no one was going to give me the money to do that because, you spend many millions of dollars on this thing. You could have just spent that money on doing some more lab measurements. What's crucial is knowing that you're going to sell a bunch of them or have a bunch of them available. So we've designed the system and all of the underlying components, all of the chips, everything we've designed so that we can scale them or fabricate them at scale. But the markets that we've talked about so far in the last 30 minutes or 40 minutes, none of them exist. The carbon sequestration market doesn't truly exist. There's Frontier, and God bless them. Patrick Collison was in my 804. That guy single-handedly has done more for carbon sequestration than most people on the planet. And with the efforts of Stripe and Frontier and Microsoft, they're fantastic. But that's not a market. That's a beginning. That's the very early roots of a market. And it is definitely not a scale market. And so the challenge for us is, on the one hand, transitioning over to scaled manufacturing things. But before we even get to that, it's who are the adjacent markets for whom this kind of technique and this product set solves a real pain point, so that we can pay for that development of the products and the technology while we're waiting for carbon sequestration to start really cooking. And it's going to be a while. The reason we are working really hard to try to satisfy the needs of our friends in carbon sequestration is not because they're going to be able to make us a VC scaling, growing company in the next year and a half. Everyone's struggling. Like, everyone's at a startup stage. The market is just beginning. It's that we need to be working with them now to establish the trust, so that 3 years down the road, 5 years down the road, when the market does start hitting, we've got the glove ready to catch the ball. We're closely tied in with these companies, and they know they can trust us. And that's deeply where we are. But as far as paying the bills, this is not it would be a bold and saucy undertaking to assume that carbon sequestration is going to pay all the bills for the next 5 years.
I see. That's kind of the ultimate market. You expect that'll be the big market to scale with, but you have other applications that are kind of your stepping stone. What are those? Just to spend a second on it.
I'll launch out one really important one, which is that, while it's true that the carbon sequestration market is not a truly mature market yet, a lot of the same people and a lot of the same organizations are interested for a whole host of reasons in measuring carbon chemistry in the ocean broadly. There are ghost ships all over the place that are doing all sorts of measurements constantly. There are a whole bunch of applications that are largely overlapping sets of people and organizations where this kind of measurement capability is already valuable. So research and monitoring broadly, that clearly already exists. And there are a host of similar things.
You mentioned the importance of kind of independent verification. As this carbon removal market scales, it's going to be important that it's not just the carbon removal companies doing their own measuring and reporting on the removals. I think that might lead well into the question of what your business model is. What will you actually be selling once this market does take off, and who will your customers be?
Oh, that's such a good question. I'll say it right off the bat. I think a lot of people have ideas about what the eventual shape and form of the carbon sequestration market is going to look like. Who's going to control protocols? Who's going to control auditing? Who's going to control measurement? Who's going to control modeling? All this, what is the shape of that industry? Which part is nonprofit? Which part is for-profit? Which part is governmental? Which part is regulatory, et cetera? And one of the things I really appreciated and I really learned early from Chris Tolles at Yardstick, that's a company I really admire and it's really great. One of the things I really learned from conversations with him was that look at other carbon markets like blue carbon and soil carbon, where initially there was a lot of we're going to structure the market this way and that way. And then eventually the buyers were like, here's how you're going to structure the market. And lo and behold, the market is starting to structure according to the desires of the buyers. And I think the same thing is going to happen here. So I just want to mark at the beginning that these are very early stages for this market. And anyone who feels or anyone who tells you that they know exactly how it's going to play out, just have some patience, because they may be right, but I think there's a lot of uncertainty. So we're trying to structure a lot of what we're doing with that uncertainty in mind. Certainly I am. With that said, let me make a really key point that drives a lot of our thinking. I cannot tell you how many times something like this has happened to me and my friends and my colleagues. You build a sensor, it gets put in an instrument, it goes out on a ship, the ship goes to sea, it gets dropped in the water, eventually gets pulled out of the water, someone pulls it back onto the boat, someone else pulls off the instrument, someone else opens up the instrument, pulls out an SD card. Eventually, someone emails you an email that says, hey, Allan, can you please calibrate the data in the attached file? And the attached file is ph_March 13th_2021.csv. And there's a list of numbers inside. And the answer to that is no. No, I can't calibrate that. It's like, it's an you've just spent millions of dollars on a list of numbers that don't mean anything anymore because I don't know when that sensor was calibrated, how it was calibrated. I don't know what the conductivity or the temperature or the depth, like where, when, who, where did this go? And so the traditional thing in it for an academic is to then go and email and try to figure out like, okay, what vessel was this on? What was the nearest CTD trace? Can we extrapolate? We do some modeling, like all that. None of that scales. But also like, it's just a deep misunderstanding of the problem. That should never happen. And if we're going to be putting, and we have millions and millions of dollars in developing a sensor, I don't ever want that to happen to our data. So from day one, the way we thought about what we're building is we're not building a sensor that we will hand to someone. We're building a sensor that is fully, like, it's not just alkalinity. It'll measure alkalinity, pH, CTD, and a host of other things so that we can do all the calibration without having to we don't spit it out and then you have to go to the back of the user manual and figure out the equation to plug in the salinity. Like, none of that. We will properly calibrate all the data. So that's the first thing. But the second thing is, as long as we're putting all that effort in, look, we know this sensor from absolute bare silicon all the way out to data. And so no one's going to be able to QC these data better than we are. So the way we're building all of our systems is they collect the data, they do the internal calibration, and they have the telemetry built in to wire the data home, depending on how applications for different deployment styles changes, but the details change. But the basic gig is, as soon as it's physically possible, the data come all the way back to us, and they're connected. And then we provide the QC. And when I say we provide QC, you click on a data point that says the alkalinity was 2352 micromoles per kilogram. You click on it, and what you will see is not just that number, but you will see which sensor was it, what batch was it built, which part of the wafer was it on, what was the calibration method that was used, who calibrated it, what were the calibration data, what's the code snippet that ran the calibration process, where was it deployed, when did the GPS go into the water, when did the GPS come out, what was the CTD profile along the way, etc. And those things are absolutely essential so that you can tell, did it drift? Was it foul? And how do I calibrate and QC those data? Those data are only meaningful if you keep track of everything. So from our point of view, it's not so much that we're trying to control that part of this, although we are. It's more that, like, I know what happens when you don't. And I think it's a structural problem in oceanographic measurement that we put things out in so raw a form that the data can become meaningless. And most data that I've ever touched in the oceanographic world became meaningless in exactly this fashion. And I don't mean necessarily that I collected, but like any that I was anywhere near. It's really not something we can allow to happen. And so it's not something we will allow to happen. So from our point of view, the business, where this feeds into the business strategy that you're asking about, business model, is that, for example, for CDR, the way we want to approach the problem is, look, we'll work with you, CDR company, to understand what your sensing need is. You tell us what you need, and we will build the system that you need, ship it to you. You put it in the water. You know your water. You don't need us to go there and put things in the water. But we will provide to you, we're shipping you some sensors, but really what we're going to do is give you a real-time data feed that gives you a properly QC'd, completely traceable, completely secure, totally robust data stream and archive so that you can know in real time, how do you need to change the levers on your process to optimize. And also, down the road, when you sell that to Mitsubishi does an audit, there's a completely transparent, traceable process all the way back to the rawest of the data. And that's really crucial to us. So that's what we're providing, is that sort of hardware and data system together. Initially, that's alkalinity and pH and CTD, but that's going to expand as we go through our development pipe. We've got a whole slew of sensors that are going to be coming down the road. That's the basic business model. Now, in different industries, there are sort of slight variations on that, but that's the basic gig with wearing my CDR hat.
Your customers they're paying for what they want in the end, which is the data, and they don't have to they don't have to deal with the hardware and interpretation of the data.
They don't have to hire an oceanographer to do the integration and then do the QC. Like, that's not their job. Their job is not to do the most unpleasant part of the oceanographic measurement. Their job is to sequester the carbon. Our job is to measure it. So we'll measure it as precisely as we possibly can.
We've talked about how nascent this market is, and I mentioned earlier how much it's kind of projected to scale. We're at this really interesting time, at least in the US, with a new administration. And I've seen some recent news about big corporations backing off their net zero commitments. And it just feels like this sort of really uncertain time about the future of our fight against climate change, at least the near-term future. I'm curious, with all of that as a backdrop, how you see the future of this space. And I know this is all kind of very fresh, but like, what's your take on all that?
Oh, God. Okay. So first off, it would, of course, be nicer if the incoming administration was saying, we really need to tackle this problem. But having said that, at the end of the day, it was never really a government problem. the job is not to make things happen despite economic realities. The job is to help align economic incentives with good stewardship. And a great example of that is solar, right? The solar has dramatically exceeded predictions and in cost and installed base over and over. And some tiny bit of the early parts of that are because of government regulations. And some tiny bits of the beginning of that were worse because of the lack of good government support. It's a bit of a mixed bag, and the story is interesting. But what really mattered was that it became the most economically responsible and viable decision to make for many purposes. And boy, did it take off. And so with carbon sequestration, it's a little bit different, right? Because the carbon isn't immediately painful to anyone. It's just the shared common asset. But you see, the US it's a little complicated where that's going right now. But look at Europe. You pull a cargo container into a port in the EU and you're paying a carbon tax for bunker. All over the world, people are starting to talk to specific large, giant multinationals. And look, the national governments come and go, but their sense of what their liabilities are down the road is not dramatically changing. They know that, or they seem to believe, because we talk to them, we hear them say this, that coming down the road are regulatory constraints that are going to force a market. And at the end of the day, they're going to have to deal with that reality. I guess I'm also, buoyed isn't the right word here, but I'm also motivated by the observation that the consequences of climate change are really starting to come due, right? We're really starting to see distributions of damage that are changing and that are getting increasingly more disconcerting and financially real. And as we see that, the least expensive possible mitigations, both for adaptation and for carbon sequestration, are going to start being more and more palatable to people. We have a bad habit in the US of regulating after disasters rather than regulating before. Europe tends to regulate before the disasters. One could quibble about the wisdom of these things, but you see it in action here very clearly. And so, the political landscape is going to be fluctuating, and it fluctuates on timescales that are very inconvenient for startups, just true. But I see the fundamentals here unambiguously as going in the direction of everyone's going to, this market is going to exist eventually. The sooner the better, but it will eventually. And the question for us is, how do we stay alive and help accelerate that process? And deeply, fundamentally, we view what we're doing as eliminating bottlenecks, as enabling this industry to be more cost effective so it can scale as quickly as possible.
Yeah, it has to happen. It will happen. It's just a matter of kind of weathering the little ups and downs in the meantime.
Yeah, exactly.
Yeah. What is your vision for the future of Aquatic Labs? And interpret that however you'd like, but what do you hope the company accomplishes?
I would like Aquatic Labs to be the default answer to the question, I run an industrial activity that impinges on water, on the ocean, and I need to measure what I'm doing, both to optimize what I'm doing and to deal with regulation, both self-imposed and externally imposed. Who do I go to measure my thing without having to hire a bunch of ocean analytic chemists? And I want Aquatic Labs to be the default answer to that across all measurements. And the reason is because we're taking this seriously in a way that I like. All the work I'd done in academia drove me towards a place of there's a thing possible that's not happening. That's what I want Aquatic Labs to be doing. But the more grandiose thing is this. Look, oceanography is amazing. I came into this from theoretical physics where we have 100 billion data points per question. In oceanography, these people measured the circulation, deduced the circulation of the Atlantic from like 6 data points, right? The cost of every single data point is astronomical. It's 6 months of people's lives and they're out on ships for millions of dollars, right? And you take this tiny, incredibly difficult to get data set and you just extract every bit of information out of it possible. And that's how we've learned most of the things we know about the ocean, whether it's eDNA or the circulation of the Atlantic. This stuff is hard and it comes from just incredibly creative and thoughtful extraction from tiny data sets. That's Herculean and it needs to change. And I really deeply want to see oceanography change from a deeply data impoverished community and field to a swimming in data, overwhelmed with so much data we don't know what to do with it field. Because what's possible when you measure more, it changes in character, it changes in quality, it changes in kind. It's not just that 10 times better measurement is 10 times better. 10 times better measurement changes what you could possibly measure, right? If you could measure 1,000 alkalinity measurements at 20 points around your field, your operation, or your coral reef, how would that change what you could measure, what you could sense, what you could actively do and control? And I think our ambition is really about changing the way we do oceanographic measurement. It's incredibly audacious. Like, I feel a little silly saying it publicly, but like deeply, that's true. We should be measuring deeply. We should be measuring pervasively at scale. And the only way you do that is you start with the assumption you're going to build millions of something. If you start on the assumption you're going to build 6, you're done. You've already failed. But if you start with the assumption you're going to build millions of something, and you only allow yourself the tools that could go to scale, now you've got a chance. And so that's the real ambition for Aquatic Labs, is to help enable a whole new way of doing massively scalable data sensing measurement in the ocean.
I love it. Okay. I have 3 questions that I ask everybody at the end of every episode. The first is, how optimistic or pessimistic are you about the future of the planet and why?
Oh, I am super optimistic because, look, there's so many people out there who are recognizing the scale of the problem and bringing to bear tools that respect that scale. I see a huge amount of potential for everything from solar, nuclear, wind on the energy production side, and also carbon sequestration in a variety of different schemes, increasingly scalable. And I think looking at a carbon, just straight climate problem, I just see a huge alignment between economic incentives and good stewardship and responsible control. It's scary to watch the political reality fluctuate, but we got to accept the fact that it's going to fluctuate, and we got to integrate across those fluctuations. And so the timescale for deep tech is decadal, and that's sort of, it is what it is. But I'm very optimistic. I'm way more optimistic today than I was 3 years ago.
Awesome. Who's another company or individual doing something to address climate change that's inspiring you?
There's a long list here I could go off. Carbon Run. So one of the challenges with carbon sequestration is that it's nice to just sequester carbon, but the market doesn't exist. But if you do something else that's independently awesome, and by the way, sequester carbon, fabulous. So Carbon Run, the team there is amazing. Jess Adkins at Calcaria. Oh, so wonderful human being. Oh, okay. You should. Yeah. So they're doing really good work. And he's a professor who, like me, he's on the sort of like geeky, wants to get technical on everything side. And both of us did not come into this thinking like, oh yeah, I grew up wanting to be an entrepreneur. But both of us are like, oh my God, this needs to get done. And I see one little tiny piece of the story that maybe has a long tail, but like I see a part of it where I can do something and how I'm going to do it.
Cool. I'll look them up. Last one is, what advice do you have for someone not working in the climate change sector today who wants to do something to help?
Ooh, fun. So one thing is that it's really easy to think of climate change as a technical problem, and it is. There are all sorts of technological problems in there, but it's as much about systems as anything else. In fact, if we solved all the technological questions, we still wouldn't have a solution to the problem. There's social, there's economic, there's a whole slew of problems. So for folks who haven't got involved but want to, I would just say you've probably got a superpower that you can use to help align economic incentives with good stewardship and climate responsibility, even without directly like getting into the technology side of things. There's huge regulatory, financial model. There are all sorts of key questions. But if you use as your North Star, like how do you align incentives with good responsibility, I think that's a really powerful attitude to take regardless of where you're coming in the field. I would also say, like, it's such a big problem. Be audacious. Even if you feel a little silly saying things in public on the scale that you're imagining, CF my earlier comments, right? Like, this is a problem that requires knocking it out of the park. It's not that there's going to be one solution that solves climate, right? There are going to be 2 to 5% solutions, and eventually we'll cobble together a solution to the problem because everything's expensive. And so you find your little place where it's cost effective. But you have to swing for the fences here, man. You cannot do a small thing and be satisfied because a small thing is irrelevant. It's got to be global scale. It's got to be able to go to scale, or it doesn't matter. Now, that doesn't mean that your thing has to go to scale, but you and your 100,000 friends together doing a thing had better be a scaled impact on the ecosystem, and otherwise it doesn't matter. So focus on scale, and sometimes that means the technology, and sometimes that means a community. Just build a big community, people doing a small, simple thing and have a 1% effect. Fabulous. Now you matter. So be audacious. Oh, and if you want to be audacious with us, we have some job openings here at Aquatic. It's a very exciting time for us. So go to our website. There's a link and apply. We're looking for software engineer, business development. And we also have an open application process because you just have no idea who you need and you have no idea when you need them.
Yeah, cool. I love it. Allan, that was really fun. Thank you for everything you're doing. I learned a lot today. Appreciate it.
Dylan, thank you so much. It's been a pleasure chatting with you, and I'm looking forward to following up.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.